She noticed it.
So many things happening right now. Actually, Sarah, could I ask you to put the link to this webinar into our Facebook feed? Thank you. Thank you, thank you. And so let's, Ruby, do we want to try one more time and see if there's anybody, if you would raise your hand, if you would like some interpretation, we'd love to help you with that.
Sí, hola, buenas noches, gracias por acompañarnos. Si necesita interpretación en español, por favor levante la manita que está al final de su pantalla para saber que sí necesitaremos el servicio de interpretación en esta noche. And I don't see it, but I'll hang out for a little bit and I'll keep...
I do see one.
Oh, yay, there it is.
Okay.
And then I'll send you the link so that if they want those in the PowerPoints as well, I'll get those to you. All right, so shall I start it?
Yeah, and then let me just one final announcement.
Okay.
Para aprender la interpretación, al final de su pantalla tiene que haber un mundo o un un mundo. Seleccione la bandera de España y así usted va a estar escuchando la presentación en español. En unos momentos ya me van a dar el acceso a la interpretación. Gracias.
All right, are you ready for me?
Yes, please. Can you enable interpretation? Thank you.
Yes, there we go. All right. Hi, everyone. Lots of moving parts, and there's lots of moving parts because we want the maximum amount of people participating in the STEM Expo this year. We want this to just be an amazing event. We want preschoolers all the way up through high school. We also want to let people know that you don't have to go to a U46 school in order to participate in the STEM Expo. You just have to live within our boundaries. A lot of people have already asked us, how do we register for this? So in December, we are going to send you a link that you will use to register, you can either contact our office directly, and I can send that link to you. It'll also be in all of our U46 information, and if you signed up to get the information for these events, we will also send you the link. And then near the end or at some point, we'll give that Google link again so that you can get signed up. So mark your calendars because the STEM Expo is March 20th, 2021. The purpose of our kickoffs is to give you a little bit of an overview of what these look like, but mainly it's about giving you ideas and introducing you to really cool people like we have this evening. There are 7 cross-cutting concepts that scientists use, and you know what? I'd be really interested to ask a paleontologist, Carrie, which cross-cutting concept and which scientific, and you don't have to answer it right now, and which scientific and engineering practices you love, and maybe if there's one that you don't love, like maybe there's a practice you don't really love that well. But all scientists use these cross-cutting concepts, and all scientists use scientific practices. So today we're going to give you some ideas for 2 of our cross-cutting concepts, systems and system models, and then also scale, proportion, and quantity. Could you, Ms. Hernandez, could you? Thank you. Here are our 7 cross-cutting concepts. And so far we have covered patterns, cause and effect, structure and function. Next week, we're going to do stability and change and energy and matter. So come back next week, the 25th. You're going to meet more really great scientists and people who care about our community. And you're going to learn some more projects that you could potentially do. Next slide, please. And here are your science and engineering practices. You know, a really common question I get right now, because we're in the pandemic and we're not face-to-face, is parents and other people very concerned that we're not able to do science because we're not face-to-face. Part of that is because when we think of science, we very often think of the science and engineering practice listed at number 3, which is planning and carrying out an investigation. But planning and carrying out an actual investigation is just one of all of the scientific practices that we use. And so here in U46, we're focusing and supporting our teachers to work through the cross-cutting concepts and all of these science and engineering practices. And this year, you may or may not be able to do an investigation, plan and carry out an investigation, unless you do the STEM Expo, and then maybe you could. But we are always doing and working on our science practices here in School District U46. And so just want to reassure everybody that we're still doing science, even though we're in the grips of this pandemic. Next slide. So without any further ado, we're going to look and investigate systems and system models. And then we're going to investigate scale, proportion, and quantity. I do want to tell you that we might go a little bit over today. We're scheduled to end at 7, but we got a lot of fun stuff scheduled for you. And we want to make sure that we also answer questions, and we'll stay on at the end to answer your questions as well. So paleontologist Carrie, I'm going to stop this presentation and we're just going to make you the speaker view. And we are so excited to learn from you. I think when you talk, it'll make you big. Let's see.
Thank you so much for having me.
Make sure, are you going to tell us a little bit about yourself?
I will. Am I big?
You're big now.
Okay.
I believe you're big.
So, hi everyone. My name is Carrie Levitt-Buzian, and I'm a paleontologist at the Natural History Museum of Utah. What's really awesome is I'm actually a product of U46. So I actually grew up in Bartlett, Illinois, and I went to Centennial, and then I went to Eastview, and then I went to Bartlett High School. So U46 is near and dear to my heart, and Mrs. Hernandez was actually one of my teachers. So I'm very honored to be here today and to talk to you about paleontology and how important science is, and show you what I do. So I'm the collections manager of paleontology here at the Natural History Museum of Utah, and I'm coming to you live from this awesome room, this paleontology collections room, and I'm surrounded by fossils. I'm surrounded by over 65,000 fossils here, and I'm in the aisle that I call the oversize aisle because dinosaurs tend to be large. And I'm going to show you some of my favorite fossils behind me, and then I'm going to talk a little bit about those cross-cutting concepts that we were talking about. Yeah, and then I'll take some questions because I know a lot of people have a lot of dinosaur questions that they'll want to ask. So I guess part of being a collections manager is I have 3 different roles. I go out in the field, usually almost the entire summer, I'm out in the field digging dinosaurs. We dig primarily in Utah, Wyoming, Nevada, and New Mexico. And we do amazing things. Sometimes we get helicoptered into the sites that we're excavating, the places that humans haven't been before. And then we get left there for 2 weeks, and then we have to hike out, find our way out. I also go to places where I have to rock climb to get up to the sites that I'm excavating. So that's kind of cool. And then every time we collect something in the field, we have to bring it back to our museum where it gets cleaned up in the fossil prep lab and glued back together, and then also kind of reposited with me in the collections. So I like to think of myself as the librarian, but for dinosaur bones. So I'm in charge of everything that comes into this room or leaves this room, whether we get it from the field or off of exhibit or off loan, or anything that we mail out to people to do research all over the world. And then I also do my own research. So I am an expert in how ceratopsian dinosaurs, like the one behind me, grows, how it used to grow. I have to think about them as actual animals, which is pretty challenging because dinosaurs, like you think of them now, don't really exist today other than in birds. And it's hard to look at a bird and think dinosaur. So I actually cut open the bones of dinosaurs and look at them under a microscope to figure out what their metabolism was like. And so I'm an expert at doing that, and that's how I figure out whether the dinosaurs were warm-blooded or cold-blooded. So yeah, those are some of the fun parts of my job. I'm going to show you some of the cool dinosaurs behind me, and I'm going to try not to lose you with my internet connection. So again, I'm in this awesome room called the collection space. So you can see it's just a huge warehouse, shelves and shelves and shelves of thousands of fossils. And I'm in charge of the entire room and all the fossils in it. So here is a really awesome dinosaur. This guy is called Diabloceratops. And those of you watching might know what Diablo means. It actually means devil, Ceratopsian. And it was named that way because it has 2 horns on the back of its head. And then also when it was excavated, it was actually lit on fire to cure the glue to make it solidify. And so it added to the lore of Diabloceratops being lit on fire. So here's what we have. It's the only one in the world, which is really cool, and that's called a holotype. The first one, and everyone has to base it off of the one that they found. So we're looking this way. So we have a big nose here. So think parrot. We were using the bird analogy earlier. Think parrot. And then we have teeth in life position, which is really rare because that's one of the first things to leave after the animal dies is its teeth. And then we have an eye hole. And then we have a horn over each eye for Diablo. And then we have a horn out of its cheek. And then a hole here, and we think that's where the ear went, but that hole isn't supposed to be there. So it either got bit in the face by like T-Rex, or it had a bone disease. And it's really interesting because this is the only one in the world, and we don't have the other side of the face. So it took us a while to realize that hole wasn't supposed to be there. And then it has this really cool spike on the back of its head. Now we only have one half of it, but we can assume everything in nature is symmetrical, so we can make up the other half of the head that we don't have. So this guy is 79 million years old in the Cretaceous, and it was found here in Utah. And I'm going to show you another really awesome ceratopsian dinosaur. So again, think Triceratops, the ones with the horns. So here's another cool one. This is Cosmoceratops. Again, the best one in the world, the holotype for it. And again, it's facing the other way. So we have a big nose here. So it's facing that way. Big nose. The jaw is in life position, which again is really rare because that usually falls off. The teeth are in life position, which is really neat. And then this guy was called the horniest dinosaur ever because it has the most ornamentation of any dinosaur ever found. So we have a horn on its nose, a horn out of each cheek. You can see it's pointing towards you right here. A horn over each eye, and then a bunch of horns on the back of what we call the frill. So the back of the skull is called the frill, and it is pretty amazing. I'll be talking a lot about how we use modern animals to try to predict in a scientific way what dinosaurs would have looked like. But for that one, for all the horns, those horns would have been covered in keratin, like what your fingernails are made out of. And so you can think of a modern animal that has that in a sheep, bighorn sheep. So I have this bighorn sheep sheath. So you have to use your imagination, and every time you see one of those horns, you got to put a keratin sheath on it, which always makes me wonder, did it have like ingrown horns, like we have ingrown toenails sometimes? So it's very interesting to think of them as actual animals. I'm going to walk you over here to see a couple more things. A lot of people ask me what's the largest thing you've ever excavated, because dinosaurs tend to be big. And if you think about the dinosaurs that have the long necks and the long tails, you think of sauropod dinosaurs. And so this is one leg bone, the femur. So the bone that goes from your hip to your knee of one of those sauropod dinosaurs. So largest creatures of all times, longer than 3 school buses put side to side or front to back. And then I'll actually show you its neck vertebrae. So if you were to feel your neck, you can feel the bones in your vertebrae of your neck, and they're actually pretty tiny. They're about that big. And look at these things behind me. Those are 4 neck vertebrae of the largest dinosaur of all times. This one's actually from Apatosaurus, which is a sauropod, just like the ones I'm talking about. The new species of sauropods come out all the time, and they're always competing on which one's the biggest. And they have the greatest names like Seismosaurus and Titanosaurus and all these scary things. I'm going to show you one more cool fossil over here, and hopefully I can maintain internet connection as I go over here, because this one is totally worth it. So that, my friends, is a relative of T-Rex. That is Teratophonius currii. And you can see it's got really big teeth. Some of the teeth are as big as bananas. So they were definitely carnivorous with those sharp pointy teeth and serrations. You can see I put a googly eye where its eyeball should go, because sometimes people can't tell which hole the eyeball is supposed to go in. And again, thinking about these as creatures, we have to figure out, did it have lips? Did it have whiskers? We see these holes right above the teeth, and we think it's either for lips or whiskers, but we don't have those fossilized. Tissue is really hard to fossilize. And so we have to use educated guesses to figure out if they had lips or whiskers. So I'll go back to my seat here and show you some more fossils. So in thinking them more like animals, that's kind of challenging to do, because like I said, their terrestrial dinosaurs aren't around today, but they share a common ancestor with crocodiles, and then their descendants are birds. And crocodiles and birds are so different. Crocodiles are cold-blooded, and birds are warm-blooded, and they're all different colors. And so we have to use the scientific process to try to figure out what colors were dinosaurs. And so many times they depict them as green, and green is like the least common color of anything in nature other than plants. And so that's kind of funny to think about. An artist made this rendition of Cosmoceratops, but we have no evidence that it's blue. But what we do have is actual skin impressions that get preserved. So here are some dinosaur skin impressions that we have to try to think about them as real animals. Because for me, like things like mammoths and mastodons are easy to think about as mammals. They're like elephants. Okay, we can see elephants at the zoo or in Africa, but it's harder to think of dinosaurs as animals. And so we actually get fossilized skin impressions, and you can see there's wrinkles in there. You can sometimes see patterns. I have another piece here, and you can see it looks way different. So here's another piece. These ossicles that make up the skin are about the size of a dime. So they're a lot bigger than the ones I just showed you there. And so we actually do get lucky and get soft tissue preserved, and we can figure out the patterns. Sometimes they have heart shapes along their back, their spine, or really big diamond shapes all across their spine. The one kind of dinosaurs that we do know what color they were when they were alive are the theropod dinosaurs, so the meat-eating dinosaurs that walked on two legs. They all had feathers. And so we actually think that dinosaurs started out hatching out of the egg with feathers. It kept them warm, proto-feathers. And sometimes the feathers are preserved. So this is a cast of a really famous dinosaur called Archaeopteryx. And it is kind of like the link between dinosaurs and birds. And it's got some of the characteristics of both. It has these beautiful wings, and you can see the impressions of the feathers. It has a mouthful of teeth, which is terrifying. If you can think of like a pigeon with a mouthful of teeth, that would be terrifying. So it has the characteristics of both dinosaurs and birds. Here's a real fossil feather that we have, which is really awesome. And so how we can figure out colors based on the feathers is if you were to look at this under a microscope, you can look for cells called melanostomes. And if you can compare those cells to modern birds, you can figure out what color it is. So we know that the dinosaurs related to Velociraptor had black feathers, gray feathers, white feathers, and a tuft of red on its head. So that's pretty neat. So when they're preserved with feathers, you can tell what color they were. Again, one of my favorite things about thinking about these dinosaurs as animals is, they had to eat, they had to drink, and they also had to poop. So we actually have some fossilized poop, which is very exciting. And no, it doesn't smell, and it's actually not squishy. It's hard as a rock. It's been fossilized, so it's been turned from its organic composition into a rock. But you can tell a lot of things about the animal that made it. Unfortunately, we don't know who dung it, but we can tell that it's a carnivore, because carnivores, for lack of a better term, pinch it off. So it's got these pinching things on the side. And then if you look really closely, you can't see any fibrous material. You can't see any herbivorous stuff. So we know that the animal that ate this wasn't actually eating plants. So it was eating meat. So that's another way that we can kind of think of these animals as animals. They were dinosaurs, but they're animals. So that's pretty neat. Another thing we have to think about when we're thinking about dinosaurs is the world in which they lived, because our world has changed throughout time. Where Utah is today isn't where Utah used to be. And Utah used to be lakeshore property at the time of the dinosaurs. We had a big inland sea during the Cretaceous when the dinosaurs lived. And so we have to kind of build up their ecosystems and what they lived around. And so sometimes we're lucky enough to get fossilized plants that can tell us a lot about the ecosystem. So I have a couple of those right here. We have fossilized wood, which is really neat. That can tell us if there were forests back then. They can tell us the animals that burrowed into the wood. So that's interesting, what the herbivores might have eaten. And then, of course, the carnivores would eat the herbivores. So it's a whole big ecosystem that we have to kind of use scientific evidence to figure out what the ecosystem was like. And then here's another spectacular fossil. So this is one of my favorite plant fossils that we have in the museum, and it is actually a relative of a willow tree. And so it actually has both leaves and flowers on this fossil. And so it's when things are preserved like this, we can figure out what their ecosystem was like, what the herbivores might have been eating, what the world would have looked like when these animals were stomping around. And I think that's very cool. So yeah, so those are some of the things I wanted to show you. We are always trying to use evidence to try to figure out our claims. We have one controversy, the ceratopsian behind us. We think that it's an adult, and we have a lot of scientific evidence to prove that it's an adult. But the researchers in Montana, for example, think it's a juvenile, and they have their evidence built up to prove that it's a juvenile. And so scientists do actually debate all the time. And so we actually work together and debate to try to learn more and more about these animals. And then I was talking about my research as I cut open dinosaur bones and look at them under a microscope. I do that to try to figure out the metabolism, the age of the dinosaurs, but a lot of museums don't like that practice. You spend so many hours digging up dinosaurs in the field. Sometimes it takes years to dig something up, and then I come along and cut them open. And our museum definitely thinks you learn more about the individual animal by cutting it open than you do by not cutting it open. But that's another technique that some scientists are pro and some scientists are con about. I'm lucky that we're pro here for that. Yeah. So anyway, that was a lot of really cool stuff. I would love to answer any questions that you guys might have. And thank you so much for listening.
There are a couple questions in, oh, sorry, go ahead. You go ahead, Peggy.
No.
There are a couple questions in the chat. Did you want me to read those to you?
Sure, that would be great.
Okay. So one of the questions is, does the poop turn into stone because it was there for a long time?
Yeah, so that's a great question. So the process of fossilization is really cool. So you have something like poop, like it would start out smelly and squishy, and it would hopefully be covered up really rapidly with sediment or sand, similar to, I guess, what your cat does in the litter box. and that will stop the process of degradation, but start the process of fossilization. And so that happens with any fossil, whether it's a fish fossil, dinosaur fossil, a poop fossil. If it's exposed at the surface, it's exposed to sunlight, it can melt, it can degrade, it can dry out, it can be trampled on. You can have a bunch of sauropods coming and trample on it and it won't be fossilized. But if it has the perfect environment of getting covered in sediment with a little bit of groundwater, the sediment protects it, and then bit by bit, that groundwater that's heavy with minerals changes the organic composition from the organic stuff to mineral. And so everything in here, except probably the mammoth stuff, is rock. It's all turned to stone, but it's through this process called permineralization.
So there's a dinosaur in here. I don't know what it is. A student says it's their favorite fossil, Dunkelus. How would I say that? You know what it is? You probably know what it is.
Dunkleosteus, yeah.
Aha.
We do not have any Dunkleosteus specimens. We do have other sharks in our collection, which is pretty neat. We have this one called Helicoprion. If you Google helicopter shark, it's amazing. It takes its teeth and it actually grows out like a fan, and it has its baby teeth on the inside of this whorl and the adult teeth on the outside of its whorl, and it's like it has a mouth with a bandsaw of teeth in it. It's crazy. So definitely Google Helicoprion or helicopter shark. It's crazy. And I think the next question is, what is your personal favorite fossil? I love the ceratopsian dinosaur behind me, Cosmoceratops. I think that is amazing. It's the coolest one in the entire world. There's only 3 in the entire world, and that's the best one. When National Geographic came to film us, they took pictures of that, which is really important. But I do actually have another favorite fossil in here, which I forgot to grab, but it's a femur bone. So again, the bone that goes from your hip to your knee, of an Allosaurus, so a meat eater from the Jurassic. But what's so cool about it is it's broken in half, and inside it's been fossilized with amethyst crystals. And so it's bright purple on the inside. So it's like a bonus fossil with a geode inside it.
Amazing. Next question is the big one. Do you know how dinosaurs became extinct?
Yeah, so there is evidence that it was because of a meteor coming from outer space and hitting somewhere near Mexico. We have the crater, we have the hole where the meteor hit. And then you have to think about what that would do. The actual impact of the meteor coming down wouldn't have killed the dinosaurs, but it would have brought so much debris into the sky that it would have blocked out the sun. And if you block out the sun, the plants can't grow. If the plants can't grow, the dinosaurs that eat the plants can't live. And then the dinosaurs that eat the herbivorous dinosaurs, they also go extinct as well. And so we think the big one is the meteor hit. And then also during that same time, there were a lot of volcanic activity in India. And we think that that also brought about the demise of the dinosaurs. So it's kind of the straw that broke the camel's back. Again, the volcanoes would send up a bunch of ash in the sky, blocking out the sun. And so that was a double whammy for the dinosaurs, and they couldn't really survive that.
Amazing. And many scientists agree with all those pieces of evidence that makes them agree with that claim that dinosaurs went extinct probably because of a meteor. And I'm one of them. The evidence is there and I can't argue with it. It's very real. Okay, we have some questions in the Q&A. One is, do you find feet of dinosaurs?
We do find the feet of dinosaurs. Sometimes the feet bones, the bones in the feet and the toes roll. And So sometimes we don't find them, the tiny bones that roll, but sometimes we do. So we do actually find feet of dinosaurs.
Wow, you meaning like they're round little ball-like bones that while you're digging, they'll just kind of roll away and just look like any other stone.
Yeah, or over time, if you have something that's cylindrical, it'll roll down the hill, and if it's really, really heavy, it's less likely to move. But if it's cylindrical, it can roll down the hill, 75 million years ago or yesterday.
Yeah. Okay, two questions that are kind of related. And I know you mentioned this, and I heard you because I heard you say that you can look at the cells in feathers of fossils and compare them to the feathers we have today to make some presumptions about what color those feathers might have been. But one person says, do you know for sure what the color of a dinosaur is, or is it a guess? And then how can you guess the color of dinosaurs?
Great. Yeah. So I did touch about it before. Most of the time, we don't get feathers preserved. We sometimes we get skin impressions preserved, and then those don't have color in them. So we have to be really, really lucky to get fossilized feathers in order to know for sure what color they were. There was a really cool ankylosaurus. Those are the ones that are bony everywhere. Even their eyelids had armor. Found in Canada, or it's in Canada now. And then that was fossilized so pristinely that they said it had like a rusty orange hue to it. And so people are still up for debate on whether or not that orange color was the color of the dinosaur or if it had to do with the sediment that fossilized it. So when we do have feathers, we can pretty guarantee what color they are. But if we don't have feathers, then it's an educated guess.
Yep. And I like that you said educated guess. It's not a wild, crazy guess with polka dots and stripes. It's an educated guess connecting what we know and what we don't know. And here's a big one that I get all the time in the planetarium because we talk about the meteor hit. And he calls them rumors that dinosaurs have survived in the oceans. And I think there's a TV show or something came out this year that made a lot of people ask questions about this this dinosaur that lives in the ocean. Do you agree that that's possible?
Well, so it's a little bit challenging because we know that birds are the descendants of dinosaurs, and birds actually lived at the same time as dinosaurs. And so because of the meteor impact and all the volcanic activity, the large terrestrial dinosaurs definitely went extinct, but the birds survived. And so not all dinosaurs have died. They're birds all around us. So that's pretty cool to think about. In terms of animals living in the ocean, I don't think that there are any dinosaurs that live in the ocean. Dinosaurs, by definition, are terrestrial. So we separate them by terrestrial dinosaurs and avian dinosaurs and marine reptiles. So they're separated that way. There are a lot of creatures in the ocean that we have never discovered yet, or things that we think that went extinct, but didn't that we just found, in markets and places. But I do not think that there are any dinosaurs at the bottom of the ocean. I often get asked, is Jurassic Park possible? And I think that question's kind of related. They're finding some really neat frozen animals from the Pleistocene in Siberia. So they're finding like mammoths in ice cubes, and they're there. They have hair. You can donate your hair dryer to thaw out a mammoth, and they have the skin and the stomach contents and the DNA. So if you wanted to make Pleistocene Park about 12,000 years ago, you can do it tomorrow. If you're wealthy enough and want to buy a lot of elephants, you can make Pleistocene Park tomorrow. But you can't make Jurassic Park because there's nowhere on this earth that has stayed the same or stayed frozen since the Cretaceous. So unfortunately, I don't think we're close to making Jurassic Park. There are a couple of researchers that are trying to modify a chicken to have dinosaur characteristics. And so we might have a modified chicken dinosaur running around, but it'll still be a modified chicken, not a dinosaur.
Well, in either case, I don't think I really want to be in a dark alley with a chicken dinosaur.
No.
Okay, last question on the Q&A. Since the meteor hit, is that why the dinosaur bones need to be dug up to be found?
Okay,
Yeah.
I can see where that would be thought of. So many of the dinosaurs. So dinosaurs lived for a very long time, from about 212 million years old to 65 million years old. So that is a huge group of time, space of time. And so dinosaurs that lived in the Triassic, so there's 3 different time periods, Triassic, Jurassic, Cretaceous, we're still digging up stuff in the Triassic. And so all of those dinosaurs had been preserved under rock. That was called a depositional environment. There's a bunch of sediment for a long time piling on. And so we're actually digging up the dinosaurs because they were preserved millions of years ago in the sediment, not because of all of the dust that would have been blocking out the sun. That's a great question. We can actually find that dust, that iridium layer, exactly the layer all across the world of what actually came down from after the meteor hit. All the dust came down and all landed on one thin little strip all around the world. But that's not why the dinosaurs are under sediment. Good question.
There's a question that was kind of skipped, but you kind of already answers it, because the question is, have you seen any megalodon shark fossils? And that's the water dinosaur that is, there must be a documentary, a quasi documentary out about it, because I've had
so
lots of
megalodon-
questions. It's the same thing.
Yeah, it's not actually the same thing. It's a different type of shark.
Oh.
Megalodon, there was a big movie about it a few years back. And Megalodon is an amazing shark. It was huge. Like, I could fit into its mouth without it closing. Like, its teeth were the size of pizza. Like, one tooth was the size of one pizza slice. It was insane how big they were. Have you ever seen one? Yes, I've seen one. I actually have one, which is kind of fun. But what I think is funny about it is that everybody calls it megalodon, but the actual species name is Carcharodon megalodon. And when everybody just talks about megalodon, it's actually a species of snail. So I like to think everybody really cares about fossilized snails and not the shark.
Wow, that is a lot of great information. Now, there's a really good question here, and you already kind of answered it, but it's really good. What is your take on the ceratopsian behind you, adult or juvenile? So they must not have heard about the argument between Montana and Utah, the scientific argument, and how does your museum organize their collection? And how would you recommend going about education for the field of paleontology? So 3 big questions.
I'll take them one at a time. So regards to the ceratopsian behind me, when I cut open dinosaur bones, what I'm looking for is actually lines. So think about when you cut down a tree, or if you've ever seen a cross section of a tree stump, you can count those lines, and those lines tell you how old the tree was when it died. And it can also tell you if it was a good season, a rainy season, or a dry season, and how fast it grew. And you can tell the same thing with dinosaur bones. And so you can actually count the lines to figure out how old the animal was when it died. And so ceratopsian dinosaurs, like the big one behind me, they can have as many lines as 28 lines. So we know that at least the large ceratopsian dinosaurs reached the age of 28. And so using that evidence, I am saying that I think that it is an adult. Plus, it's huge. I have to use a forklift to move that thing. And so using the scientific evidence, I'm one of the scientists who think that it's an adult. And why they think that it might be a juvenile is that they're trying to so there are 2 different trains of thought. There are lumpers and splitters. There are people who call scientists splitters, that we just want to name new species all the time, even if we don't have a whole lot of evidence that it's a new species, or lumpers, where everyone thinks that all of the dinosaurs are the same. And so we're more of the splitters kind, where we have a lot of evidence to support it being a new species of dinosaur. And so we're the splitters, and then we call Montana and Montana State lumpers, because they're trying to prove everything is Triceratops. And so they think that they have enough evidence that the Cosmoceratops grew into Vegaceratops, another large ceratopsian. And the same thing with they think Triceratops grew into Torosaurus. And I think that they're really interesting debates, because we can't just name things new species all the time. We need to have evidence saying that it's a new species. And so I do think it's valid to think, well, it could be a juvenile, or it could be a male or female version. We still don't know how to tell the difference between male and female dinosaurs. And so we do have to think of those things. And so it's really good that we're really good researchers and really good friends to have these discussions to try to figure that out. And then I think the next question was, how does your museum organize collections? That's a great question. That's my job. So how I've organized this room is by unprepared jackets. So things that still need to go down to the prep lab to be cleaned up. And they're really heavy specimens that have been helicoptered out of the ground. And then we're in the oversized aisle. So the very big dinosaurs are living right here. And then I have more of the room, of the storage room behind me, that are the smaller stuff. So first I have arranged it by prepared versus unprepared, and then by size, large versus small. And then I do it by time period. So I go through time from the oldest to the youngest throughout time. And then even within that, I do it based on different species. And so I have all the Allosaurus fossils together, all of the saber-toothed cat fossils together, all of the ceratopsian fossils together. And then even within those cabinets, I organize it anatomically from the tip of the head to the tip of the tail. Thank you for asking that question. That was a wonderful question. And then how would you recommend going about education for the field of paleontology? Find a wonderful mentor like Mrs. Hernandez. So first I'd start by researching, studying really hard in science. There's a lot of really great science classes. So, general science, chemistry, that kind of a thing. In high school, maybe in middle school, but in high school, they can get some more interesting classes like geology or anthropology or environmental studies. And then in college, there's a couple ways to go. You can usually either go the geology route, so the rocks that the dinosaurs are found in, or a biology route, like them as animals. And so I actually went the geology route for both my bachelor's and my master's. But again, you have to kind of think about both of those. So I went the geology route, but I had a steep learning curve to learn about the biology of the animals. So some people double major biology, geology. I have friends that are anthropologists and environmental studies folks who also became paleontologists. So definitely in the field of science. I think that going to your local museums and interning or volunteering in your local museums is a great way to get your foot in the door. I think that's great. There's a lot of clubs and groups here in Utah. We have the Utah Friends of Paleontology. There might be a local one near you guys about, fossil enthusiasts. I think that that's also very, very useful. So that's a good question.
Yeah, I do know that there's geology clubs around that students can join, and you make an interesting point. And similar in astronomy, there's a lot of connections to meteorology. And the previous director of the planetarium was actually originally a meteorologist, but he knew a lot about Earth and space science, and he liked both of them. So there are connections to all sciences. So I definitely agree with you. Take all the sciences, take all of them. You'll figure out the ones that you love as you go. But just because you want to be a paleontologist doesn't mean you shouldn't take biology, because you need to take biology. So we are going to move on to the stars here. And I want to thank you, Carrie Levitt, the paleontologist, for coming on and sharing what you know with us. It's been absolutely amazing. Great questions. And we're going to take a look at the stars.
All right, my pleasure.
And we're going to move on from here. You are very welcome.
Sincerely, thank you, Carrie. We're going to see if we can't get you back.
Definitely. Okay, so we're doing a little switch over to the stars, but I want to make a connection to the STEM Expo. Now, remember, anytime you learn something new about science, you always start with the phenomenon, because the natural world is amazing. But if you're thinking about a STEM Expo project, you also start with some kind of phenomenon, an amazing thing, a surprise in nature, something that happened that you didn't expect it to happen. And then you start thinking about it. Like, for example, I'm going to tell you right now, the sun is an average sized star compared to other stars. It is not the biggest thing in the whole wide world. And that surprises some people because when you're really little, you think the sun must be the biggest thing in the entire universe because it's so bright and it's so big. But the sun is an average star with average brightness. But yet I can't even look at it because it hurts my eyes and it burns my skin. So what is up with that? That's a phenomenon. So the next steps would be to keep gathering information. Think about your phenomenon. What do you know about that? What do you know about the sun? What do you know about stars? And one thing I want to go to right away is to show you that scientists, I mean, not even scientists, people way before there were what we officially called scientists, noticed that stars came out at night like this. Here we are at 4:15. The sun sets tonight around 4:25, or it did. I'm going to fast forward time a little bit, though. We're going to just let it turn to nighttime. Oops, I went too fast. When you first start being able to see stars, when it first gets dark enough to see stars, and you see maybe just one or two, those brightest stars you can see, I see one there and one there and one there. Those are called the first stars. Ancient people said, yay, they're the first stars. They're the first stars we see. They're the first magnitude stars. Magnitude is brightness. And then a little while later, you start to see more. And they, cleverly enough, they said, hey, there's the second set of stars. So they call them the second magnitude stars, the number twos. And then as it continues to get dark out, you get the threes and the fours and the fives and the sixes. Our human eyes can see all the way to a 6. The higher the number is, the dimmer the star is. A star that's considered a 7 can only be seen with a telescope. A 0 is a really, really bright star. Now, we're not in ancient times anymore. In modern times, we have realized that we can really carefully measure the light that comes from stars. And the brightest star in our sky is Sirius. It's like a negative 1.4 or something. It's like below 0. That's the brightest. And the dimmest is still a 6. That's what you can see with just your eyes. The Hubble Space Telescope can see something as dim as a 28. The full moon is a negative 11. The sun is a negative 27 in our sky. Negative 27 in our sky. That is really, really bright. It's blinding bright, as a matter of fact. So what's the deal with that? But wait, if the sun is a negative 27 and it's so bright it burns my eyes, how can that possibly work? Why is it so bright? So it leads to questions that are true wonderings, not just how many miles across is the sun? That's a fact I can look up on Google really easy. Like questions that make you observe, questions that explain things. Or maybe a question like, how is the sun so bright if it's not a very bright or big star? And it turns out that there's a very easy, simple explanation, actually. Now, it's complicated, star brightnesses, but why is the sun so bright if it's not a very big or a bright star? Well, I wonder, let me see if I can pull up the chat. Do we have any answers in there? I got the Q&A here. That's the dinosaur stuff. There it is. Does anyone have any ideas about how the sun is so bright if it's not a very bright star? Why does it practically blind us? And I see it. We got it because it's so close. It is. It's relatively close. I mean, people in ancient times figured out how far away things were by, this is a lot more information than we need right here, but they use geometry. There's a way that you can measure far away things by a person standing like here in the middle of Africa. And at the same moment, when a person down here measures where Venus is in front of the sun during a transit, they can measure these angles, figure out equivalent angles, and then figure out the distance between that object and your eye. And we know how far things are. We can even do that for close by stars. We can look at a star in January and compare the background stars to July when we look at that same star, and then there's different stars behind it, and figure out how far they are. So here's the answer. The moon is less than 1,000,000 miles away. It's actually 240,000 miles, way less than 1,000,000 miles. The sun is less than 100 million miles. It's 93 million. It's just a little bit under 100,000 miles. So how do we compare stars? How far are stars in miles? What are they less than? Well, it's absolutely mind-blowing. The scale of our solar system, the scale of our galaxy, the scale of our universe is totally mind-blowing. And if I were to have you look at one thing here. This one, if the moon were only 1 pixel. I'm going to bring my cursor over here to the right, and I'm just going to scroll. Now, here they are imagining that the moon is 1 pixel. Right there. See it? Ta-da! Like if that was the moon, this is how big the sun is. Isn't that amazing? And then we're going to keep scrolling to see how far everything is. That was about 6 million miles just now. We're going to keep going at that speed. What would the next thing be in line? We saw the moon and the sun. It's pretty empty out here. Here we go. We got to keep going. Here we are, going and going and going and going and going and going. Here comes the first planet. This is how far we have to go to get to Mercury from the sun. Let's switch this to miles. A mere 36 million miles. Let's keep going. What's the next planet? How far apart are the planets? As it turns out, things out in space are pretty far apart. It's really not like in Star Wars where they have to like dodge big rocks all the time. We'll be coming up on a new planet soon. Sit tight. Here we go. I'm still going millions of miles. Ta-da! There's Venus. But if I want to keep going, most of space is just space. I'm just going to keep going here. Okay, we're halfway there. What's the next one? If we did Mercury and Venus, wouldn't that be Earth? Ta-da! There we are. And there's little moon. That's how big the moon is, 1 pixel. So, oh, piece of cake. The next one's Mercury, right? Well, Mercury is actually, or Mars is pretty far from the Earth. It's not really that close. It would take about 7 months to go this far in a spaceship. And we're like fast forwarding like there's no tomorrow. And if you scroll through this whole thing, it takes over 5 minutes to get to the next star. That's the next star. Our sun is only 93 million miles away. Mars is only about 36 million miles from the Earth. Pluto, when we get to it, is about 4 billion miles from the Earth. I mean, 4 billion, not millions, billions. Like, this takes forever. I'm going to fast forward out to Pluto. Just like lightning. Whoa. There we are. Pluto. We still love Pluto. There it is. But wait. You'd have to scroll through 6,000 more maps the size I just did before you even see anything else visible. It's absolutely amazing. It's absolutely astonishing how huge everything out there is. So, let's see which one. That's the one I wanted. So to try to figure out the scale of everything, it makes sense that the sun is so bright because it is really, really close to us. Light travels at 186,000 miles every second. In 1 year, it goes 5.8 trillion miles. I'm just going to call it 6 trillion miles, just to round it up. So Pluto's 5.4 light hours from the sun. It's not even 1 light year away. Wait, what was our question? It's really easy when you start looking at these numbers to get totally mixed up. The sun is 8 light minutes away. It takes the light from the sun 8 minutes to get to our eyes. The other end of the solar system, it takes 2 years for light to get there. What about the next star? The moon is less than 1 million miles away. The sun is less than 100 million. Our next closest star is greater than 25 trillion miles, and that is our next door neighbor. You have to keep adding zeros to talk about other stars in our own galaxy. And just to give you an idea, in 1977, we launched Voyager to go out and look at the outer planets. And they got there, they did their thing, and they kept going. Voyager 1 and 2 have both exited the control of the sun. So they're said to be in interstellar space. They're between stars. They're not even between planets anymore. Well, how much longer until Voyager 1 and 2 get to the next star? Between 16 and 20,000 years from now. That's how far the closest star is to us. It's just mind-blowing. The sun is a star, so it's huge, but compared to other stars, it's not one of the biggest. It's just an average size one, but it's so bright in our eyes because it's so incredibly close. So the sun is very bright, but not compared to others, and that's because it's so close to us. You got the idea. So let's go do some observing. I'm going to exit here so we can go back to Stellarium. We were at our evening sky. Let's go all the way so we can see the whole thing. This really is the night sky tonight. And if you go outside now, and we're a little bit after 6 o'clock, hopefully you'll get a chance to see this. The moon, the crescent moon, just a couple days after a new moon, is low in the southwest. And right now it's 6 o'clock, so roughly an hour ago. Saturn and Jupiter were right next to the moon. The moon's probably little hard to see right now because it's below the horizon for some of you, or below the things on the horizon like trees and stuff. We got a lot of satellites again, as usual. Every night has all those satellites. I'm making time go faster, so we're able to see that those move very, very quickly. But this is exactly what will be up in the sky tonight. I think I'm going to go out a tad just so we can see more of the sky. And Stellarium's really neat because if I have a star that I want to look at and say, well, Deneb, is that one really close to us because it's so bright? I can click on it and it tells me that that is 1,411 light years away from us. That's 1,411 times 6 trillion miles. That's how far that star is. It's actually pretty far, so it's an intrinsically really, really bright star. And I could pick a dim one like that little one right there. Let's check that star. That star is 555 light years away. And this one right here, this one's 432 light years away. How far is the sun? Not even 1 light year. It only takes light 8 minutes to get here from the sun. It's way, way closer to us, without a doubt. Let's take a look at the lines for the constellations that are up right now in the west. Here's the drawings. And the names. The Great Square of Pegasus is up high in the southwest right now. Cygnus the Swan Deneb is the tail of Cygnus the Swan. And let me remove that clutter and let's look towards the left. Let's look in the south. Let's see what we got tonight in the south. Here are the constellations that are visible. That is the Great Square of Pegasus up high in the south, headed towards the southwest. Capricorn is right here. Aquarius is right here. You'll notice if I take everything off, neither one of those constellations are very bright or noticeable in the sky. It's just the way it is. Some stars are brighter, some stars are dimmer than others. And if we zoom in on this one spot here. I'm going to zoom in. There it is. I see it. I see a galaxy. Look for a fuzzy spot right here, you guys. It doesn't look like a single star. It looks more like a smudge. If I go in a little closer, you can see that. I'm going to click on it. That's the Andromeda Galaxy. That is the Andromeda Galaxy. That thing is 778 kiloparsecs. We're talking 2,358 million light years, 2.5 million light years away. That's an entire galaxy of stars. It almost looks like a single star because it's so far away. It is 2.5 million light years. That's 2.5 million times 6 trillion miles. I don't even know what that's called. I guess we could call it a gajillion because it is so many miles that there's so many zeros after it that we have to switch to light years. 2.5 million light years away. That is the Andromeda Galaxy. It is the only galaxy visible to the naked eye in the northern hemisphere, which is where we live, but you have to have dark skies, dark enough to see a 5 or a 6 magnitude, and normal suburban backyard goes to about a 3. So if you have a particularly dark backyard, you might be able to look up, you find the Great Square of Pegasus, the one on the top right, the star in the top right, I'll draw in the lines, kind of goes up this way, and right at the tip there, that's the Andromeda Galaxy right there. It's a really neat thing to look for this time of year. And then if we head towards the east, the southeast, we've got Mars. Mars has been bright for months now. It's still there. Here are the constellations that are up in the east tonight. We've got Taurus the Bull coming up. And here's the good news. 646 is pretty early. If we went to, say, 9 o'clock, we're starting to be able to see some of my favorite winter constellations. By 9 o'clock, Orion the Hunter has cleared the horizon. Here we are at 9:28 tonight, and right there is Orion, the big rectangle, and the 3 stars in the middle that are his belt. Orion the Hunter, his belt points to Aldebaran. That's the eye of Taurus the Bull, and there's the beautiful little Pleiades. You have to wait till 9:30, so a little late, but by next month, you'll be able to see it as soon as it gets dark out. And then if we head over to the north, we'll be facing the Dippers. You know, the Big Dipper, the Little Dipper. Do you see the Big Dipper? Look for it. Look for it before I outline it. And it's the Big Dipper. If you see a dipper, don't obsess over the Little Dipper because it's not very bright. It's the Big Dipper that you see right along the horizon in the north. There it is. That is the Big Dipper, part of the Big Bear. The last 2 stars in the saucepan point to the North Star, and there's Little Dipper. That is the Little Dipper. That is the North Star right there. And here are the drawings in the north. Cassiopeia the Queen is up high in the north. Upside down W, so I guess we could call it an M right now. And that is what is up in the sky for tonight. Now, I want to know if you have any questions or if there's anything specific I can show you in the sky.
A question that has come in is, how big is the Earth compared to stars?
Good question. Because that tells me that you're thinking about scale.
Mm-hmm.
And here we go. So if you look at this one, I'm gonna undo another one too, so I can look at this. I gotta unskip it. So there we go. There's the planets, and hopefully, you know, Mercury, Venus, Earth is the third one. I'm gonna get that out of the way. Mercury, Venus, Earth, Mars, and that's the sun. That's a star compared to Earth. I mean, that's the Earth right here compared to the gas giants. The gas giants are way huge compared to the Earth. But if you want to compare other stars, like remember the sun is just an average ordinary star. Well, check this out. Right there is where the sun would be. At the tip of that arrow, right there, 1 pixel, there's the sun. That's how big the sun is. And that's how big Sirius is, the brightest star in the sky. And that's how big Pollux is in Gemini. That's how big Rigel is in the bottom left corner of Orion. And that's how big Betelgeuse and Antares are compared to the sun. It's mind-blowing. In this picture, the sun is only 1 pixel. That means Jupiter isn't even visible. And that makes the Earth like less than a speck of dust in a drop in a bucket in the ocean. That is how big the stars can be compared to each other. And they're different distances. These supergiant stars sometimes are really far away, but we can still see them in the sky because they happen to be extra humongous, like way more than your average star. So if we were to go back to the west, towards the east, Betelgeuse, there it is right there. That's one of those giant stars, roughly 500 light years away, yet it's one of the brightest stars we can see in our sky. And that's because it's extra humongous. Usually distance is what tells us how bright a star is. And there's Aldebaran, another giant one in the eye of the bull. That one's only 66 light years away. And it's pretty big. So that's a pretty bright star. It's the red eye of Taurus the bull. Good question.
I have another good question for you. Today I met, I believe this is a young lady I met in 3rd grade reading in Mrs. Dickett's class. It's Sophia. And I'm thinking her question might be your project. And I know she's really excited about doing a project too. And her question is, why does the sun set? And so I was wondering if you might want to talk to her about stellarium and how she might, instead of giving her the answer, how could she answer that question?
Yes, I think stellarium, well, stellarium gives us the same view that we have from Earth. And the sun definitely rises and sets. I mean, if we could check this out, if we go to early morning, there it is. There comes the sun rising up again. The sun. So why does it do that is a great question. And one thing you would have to do is think about how do all the planets move in comparison to each other, and with the sun. And what I would recommend, and I don't have it pulled up, but I have it saved here so I can easily show it to you. It's called 9planets.org. And if it's free, it just takes a minute to load when you do the free version. And you start this and it shows you the planets going around the sun from, and it's making a sad face. I use this all the time. No, that's not the right one. It's called 9planets.org. There it goes. And it takes a minute to load, but it lets you examine the planets going around the sun at the correct speed compared to everything else. And it shows all the different movements that the planets make in addition to just going around the sun. So investigating 9planets.org might be a way for you to figure out what's happening when we look out in space from planet Earth. Now it looks like it's stuck. Try to have every question anticipated. There we go. It's going. It's just going kind of slow at the moment. But this is a good app to explore, because the other option would be for you to become an astronaut and fly out into space and look at all this. And obviously that's really hard to do when you're still just a kid. But we have these measurements that we've made of things out in space, and we can put them into apps and keep everything to the correct scale. And that's a way that we can explore things in space without actually going to space. And 9planets.org is really good at this. I'm not sure why it's not loading very quickly, but it is, because I can hear it. It's just taking its sweet little time. Maybe it's the moon one. I'll take that down.
Send that link to Sophia's teacher tomorrow so that she can get that. Here's another great question, and I'm wondering the answer myself. Is there any stars smaller than the Earth? Any stars smaller than the Earth?
I do not think that there could be a star smaller than the Earth, because that means it doesn't have enough mass to generate enough heat in the center for nuclear fusion to start. So the nature of what a star is, a humongous amount of mass that gravity collapses in the center so tight that it gets so hot that the nuclei of two atoms actually fuses together. And that process gives off huge amounts of heat and light. Can't happen unless there's an enormous amount of gravity and an enormous amount of mass. And the Earth, an object the size of the Earth, is not massive enough. Even Jupiter is not massive enough to be a star. If it were quite a bit bigger, it could. It's the same material that stars are made out of, but it's not big enough. So there are no stars smaller than the Earth, but there are a few stars smaller than the sun. The sun is an average star, so there's some that are smaller and some that are bigger.
Excellent. So this is a great question. You gave a lot of distances. You talked to us a lot about scale. And so this question is asking, well, how do we measure the distance from one planet to another? Like, how do we know that?
Well, there's actually several different ways that we know that. And that was on this slide, and I did go through it really fast. It boils down to geometry. That's what it is. It's kind of like if you have a really tall pine tree and you want to measure how tall it is, but you're not really able to climb it with a tape measure, you can measure the angle to the top of the tree and then measure how far away you are from the tree. And we use what's called triangulation to figure out the height of the tree. Well, we do the same thing with planets, and we do the same thing with stars. And far away stars, we actually have to study their light to figure out how far they are. We use a special device called a spectroscope, and it measures electromagnetic energy coming from the stars, and that's how we figure out how far they are. But close stars, we can compare the star in June and then 6 months later in January. So that's like 93 million plus 93 million miles. That's 180 million miles. Well, the angle we see that star at compared to the background changes, and we can measure that angle, and then we can conclude how far it is from us. So it's always started off with triangulation, with people making observations. And they also figured out a long time ago that planets that move faster are closer to the sun. And if you can observe a planet and notice how fast it moves in front of the stars, you can compare it to each other. You can say, well, this one is faster than that one. So the faster one is closer to the sun. So people a long time ago figured out that Mercury and Venus were closer to the sun than Jupiter and Saturn because of their speeds. Now, they didn't know the exact distances. They just knew which ones were in order. And over time, as we just deduced more and more and more and figured out more and more, we do know that the sun is 93 million miles away, and we do know the distances between the planets. It's math and geometry is what it boils down to.
A question just came in about the asteroid belt. How did the asteroid belt form?
Well, the asteroid belt is kind of like the leftovers of everything that formed planets. I'm gonna get rid of some clutter for just a moment here. What I mean is there's a lot of features in nineplanets.org. I'm even going to get rid of the stars and the lines because I want to just look at solar system stuff. Scale grid is the other one. So if I zoom out, you can clearly see the asteroid belt right there. Now, billions of years ago, rocks like this, that's what these are, they're rocks. They were everywhere in the solar system, and they were all moving around the sun in basically the same direction, but not exactly, and they would crash into each other. Gravity would make them stick. Eventually, over time, so many of these crashed together and stuck together that we ended up with 8 big rocks going around the sun. Oh, the leftovers gravitationally got squished between Mars and Jupiter, and we call those the asteroids. There's also a bunch that gravitationally are way out at the edge of the solar system. We now call that layer of rocks. That's the dwarf planets, the Kuiper belt. The dwarf planets live there. And even farther out, we have the Oort cloud, where the comets come from. So the asteroids are really leftover rocks that are the same rocks that make up planets. And most of them nowadays are trapped between Mars and Jupiter. They don't generally crash into the Earth. I know. Carrie, the paleontologist, just said one did. They did. They do hit the Earth. The big ones billions of years ago crashed into and became planets. It is not common for there to be big asteroid hits anymore. I'm not saying it can't ever happen, but it's unlikely to happen. And as of right now, there are no asteroids aimed at the Earth getting ready to cause another extinction. There are none big that are headed towards the Earth. So don't lose any sleep over that tonight.
And the follow-up question is, and this is a great one, but where were the leftovers from? Where did these crumbs of rocks come from?
Okay, our whole entire solar system, if we go way out, and we keep going out, and we keep going out, and there's all these other stars, and we are in a galaxy called the Milky Way, and it's made up of stuff, lots of stuff. This is our Milky Way galaxy. The center's real bright, lots of stars there. There's these spiral arms of stuff. It's mostly stars, but there's also these areas of loose gas and dust called a nebula. And scientists think there was a nebula in space right here that nobody knows exactly for sure why, but all that dust started spiraling around the center. It started spinning, and then gravity collapsed it inward. And then eventually a star formed in the center. We call that the sun. And all the material that was left over that didn't collapse into the sun, that's the stuff that becomes the planets. So that's the short version. It's formed in a nebula of debris, of gas, dust, and little particles. And here it is, our little old solar system, one of many.
Can you guess what the next question is? It has to do with the planets and can they crash?
Oh, absolutely not. Take a look. That's a great question, and I love to answer that one. Seriously, I'm going to have everything move. We're even going to go fast forward. Look at that. Ta-da! Look, all the planets are going. You can barely tell that Neptune's moving, or Jupiter or Saturn. The closer a planet is to the sun, the faster it goes. Let's zoom in a little more. Oh, look how fast the inner planets go. You look at them. Look, 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 look. Are any ever going to crash? No way. All the orbits of planets are parallel. Parallel, like train tracks. They never cross. That's a rule. For a planet to be called a planet, it has to be parallel with all other planets. You know what is not parallel with the planets? Pluto and the dwarf planets. That's one of the reasons why Pluto isn't a planet. All the real regular planets that follow all the characteristics of planets are parallel. And no, I have this much concern about Earth crashing into another planet in my lifetime. None. It's never going to happen. It can't happen. Planets are in parallel orbits. They will never, ever crash into each other because they all have their own road. That's a great question.
We have a couple more really quick questions. I think we'll do those and then we'll let people leave because I think we've gone over.
We have.
And then but we'll stay and answer questions that you might have specific to the STEM Expo. But these are the two more questions that came in. How come shooting stars move and regular stars don't? That's one question.
Okay, because shooting stars are not stars at all. We call them shooting stars because they look like shooting stars. They're actually little tiny pebbles, little tiny rocks, not even close to the size of a star. And they're basically crashing into the Earth. And they start on fire when they hit our atmosphere. Those are little loose pieces of rock in our solar system that didn't form a planet yet. Every time you see a shooting star, it's a little piece of rock joining the Earth and becoming part of the Earth's mass. Most of the time, though, they burn up in the atmosphere completely, and just the ashes fall down and become part of Earth. A meteor or shooting star is not a star at all. Stars don't shoot or fall because if they did, there wouldn't be any left in the sky because we get about 4 shooting stars every hour. And if the Earth's been around for billions of years, every time a star fell, we'd be out of stars already.
Is there only one moon in the universe, or is there one for every planet?
Well, there's not one for every planet, but there's one for Earth. Mercury and Venus have 0. Mars has 2. Oh, Jupiter has something like 60 or 70. All the outer planets have lots of moons, and Earth only has one moon. I mean, they're officially called natural satellites, but I know what you mean, and you know what I mean when I say the moon of others. It's not on this diagram here. I think that was a setting that I turned off to show the rest of the moons, but there's lots of moons in our solar system alone. And I think you said in our universe. Oh my goodness, there's billions and billions of stars in our universe. Each one could have planets going around it, and each one of those planets could have lots of moons. So there are gajillions upon gajillions of moons in our entire universe, if you think of it that way. But just in our solar system, there's close to 200.
So my question is, do you guys have questions for us? Thank you very much, Mrs. Hernandez, by the way, for that tremendous program.
You are welcome.
And so our question is, our staff is on with you. And our question is, do you have questions for us about the expo? So do you have ideas that you'd like to throw out there? Do you, Ria has some ideas they want to run through. Do you want me to unmute you? Will that be the easiest thing to do? So let me do that. Let me find you, Ria. Allowed to talk. Okay. So Ria, are you able to use your unmute yourself?
Yeah.
Yes. Okay. I can barely hear you.
Yep.
Okay, so I had an idea. Can I do an experiment like how much salt can make an egg float and why?
That's a good one. We can barely hear you, so I don't know if you can lean into the microphone or turn up, but I think that's a good, that'd be a good idea for an experiment.
So
And
have you ever seen that done before? Is it something that you were like amazed at when you saw it happen?
Yeah.
Yeah, if you're really interested in it and you want to know why that happens, I think that's a great scientific phenomenon for you to explain.
I also had another one. It was what would happen if the sun disappeared?
Oh.
Interesting. And that is something interesting to think about. And that is a very deep question because that's not something that can give you a one-word answer on Google. So I think that might be a good question to investigate and think about what if you come up with 100 possible things that might happen. So you're going to have a huge list of things that might happen. Do you think maybe you could look at those things that might happen and find a project in there that you could run a test on or something?
Yeah. Yeah, those were my ideas.
Those are really good ones.
Yep.
Thank you so much for sharing those too. And our staff, we can work with you. You can just I'll put my email in the chat and you can contact us. And so if you need further help with developing or want to run any other ideas by us, just email me and I will forward it to our whole team. Our whole team's on, and we can help you as well. Okay. Does anybody else have any ideas or questions? No? Well, you guys were lovely. This was so much fun. I want to thank, Carrie, the paleontologist, for being here. I want to thank Mrs. Hernandez for being here and doing this. And I want to thank I want to thank all of you for being here. And then also the entire science staff for being here. You guys are wonderful and I appreciate all of you. All right. Thanks, guys. Don't forget, we'll be here next week. Yes, thank all the teachers. You're right, Rosa. I want to thank all the teachers who also, we did have some teachers on here. We do appreciate you guys. Yep. and your support. Just really good point there. Thank you.
And encouraging you to do a science fair, a STEM Expo project for sure.
Yes, we're very excited about that. So next week, we've got another program for you. Next week, we have 4 different people who are going to be presenting stability and change, and they're going to talk about soil. They're soil scientists. And then we've got a project that you could do. It's called Start in Your Yard. So it's a project that you could do and it involves native plants in your yard. So hopefully we'll see all of you guys next week. A new flyer will come out. We'll send it out. In the meantime, you have my email. Just email me with any questions or concerns. And again, I just want to thank everybody for being here, and I want to thank the science staff for putting this together. Thanks, everybody.
Thank you.